Next is the production of 4-methylcyclohexene by the dehydration of a secondary alcohol. So to be a dehydration, it means we have to remove a molecule of water, okay, the hydroxy that makes it an alcohol, and a hydrogen from the carbon next door, and it's going to result in a new carbon-to-carbon pi bond. These are considered elimination reactions as we're pulling part of the molecule out and eliminating it. They are acid catalyzed. And to look at the mechanism. Here again, HA is just an acid. It doesn't matter which particular one. For a secondary acid, it's going to be fairly strong, something like 85% phosphoric, and we're going to have to heat it. But the mechanism. Here again, the oxygen has two unshared pairs, of which it's willing to donate them in a Lewis-Base style reaction. So the first thing that happens is that it pulls the hydrogen off the acid, okay, whether that's the hydrogen phosphate or hydronium, doesn't really matter. The thing is that we get our protonated alcohol. That does a couple of things for us. Number one, it gives us a better leaving group. If I were to try to knock the hydroxide off, the OH off here, it would have to leave us hydroxide. That's much more basic than here, where it would leave us water. Okay. In addition, then, to give us a better leaving group, it inductively makes the carbon it's attached to more slightly positive, and that inductively makes the carbons next to it more slightly positive, which means that the hydrogens on those carbons are, here again, just slightly positive, and so more acidic. So there are two hydrogen here, there are two hydrogen here. Those four hydrogen are all exactly equivalent because of the symmetry of the molecule, and there's no one that's better than another. And so I'm going to take a molecule of water from the environment and pull off one of those hydrogen. Okay. Now, as one of those acidic hydrogen accepts a new bond, it has to let go of the old bond because hydrogen never gets two bonds. So I'm going to take the electrons that used to be between the carbon and the hydrogen and bring them down to the carbon with the oxygen. Here again, if I took the other hydrogen that was on that carbon there, I wouldn't have anything to do with the electrons. As bring them over to the carbon, like over here, would have to kick off a hydride, and that's very, very basic and not something we want to do. Okay, but there is a hydrogen here, even though we don't draw it in with bond line. So that carbon has to give up something, and that's the bond to that positive oxygen. The water that pulls the hydrogen off becomes hydronium. There's plenty of that floating around anyway. The protonated alcohol leaves us water. There's plenty of that for us. And there's our alkene. Procedural notes: this reaction is set up, okay, as a distillation, as the boiling point for the alcohol is higher than that of the alkene. So as the alkene is made, it distills over. The receiving flask is put in ice to make sure and cool the alkene over as it condenses. Both acids called for are in the PDF are corrosive. So if you were doing this, I very strongly recommend that you wear aprons and use gloves. We're going to use a heating mantle as a source, and if we heat it slowly enough, here again the product should distill without the alcohol or any of the acids, so we can isolate the product that way. Okay. There will still be plenty of water around, so there'll still be liquid in the source flask boiling. We don't have to worry about that, but once we don't get any more dripping over, we're gonna shut it down, okay? The next step called for in the PDF, okay, is a second distillation to purity. Here again, that is a purification step and would be at your discretion, with the notes there on the board. If you decided not to do the second distillation, you would simply not report a distillation range on your label. You put distillation range NA, not applicable, or NP, not performed, that sort of idea. So that's our dehydration.